We have already seen that linear models have many different applications. In all the applications, the basic setup was that we have a system into which we have a number of inputs and one output. The output was always continuous, but the inputs could be both categorical and continuous. If it so happens that all the inputs are categorical, we call that situation a case of analysis of variance or ANOVA. There is a deep theory of ANOVA in the context of linear models. We are going to take a look into that in this and some of the subsequent lectures. The theory of ANOVA. A linear additive statistical model for the ANOVA is given by Yij equal to mu plus tau I plus epsilon ij, where mu is the grand mean, tau I is the deviation from the grand mean due to the group levels, and epsilon ij is the error tau. Note, the grand mean is estimated from the observations and can be denoted by y double bar. The total deviation tot ij is the difference between a data point yij and the grand mean y double bar. Tot ij equal to yij minus y double bar. For any data point yij, tot equal to tau hat plus epsilon, that is total deviation equal to treatment deviation plus error deviation, that is total deviation equal to treatment deviation plus error deviation. The total deviation is the sum of the treatment deviation and the error deviation. Tau I hat plus epsilon ij equals yi bar minus y double bar plus yij minus yi bar equal to yij minus y double bar, and that is tot ij. Notice that the sample mean term yij bar cancels out in the above addition, which simplifies the equation, which otherwise would be even more complicated than what it is now. Square deviations. Square deviations are another tool that we use in linear models to make expressions that look complicated. Tau I hat square plus epsilon ij square equal to yi bar minus y double bar whole square plus yij minus yi bar whole square. Tot ij whole square is equal to therefore yij minus yi double bar whole square. Sums of square deviations are just sums of square of tot ij. Summation I from 1 to r, summation j from 1 to n of this quantity is equal to two sums I from 1 to r, and the other sum is I from 1 to r, j from 1 to n. That is I from 1 to r, j from 1 to n of a square equal to I from 1 to r plus I from 1 to r, j from 1 to n. Therefore, SST equal to SSTR plus SSE. If you do not understand the meaning of SST and SSTR, do not worry, you will understand them later. The sum of squares principle. The total sum of squares SST is the sum of two terms. The sum of squares for treatment SSTR and the sum of squares of the error, which is SSE. Therefore, SST is equal to SSTR plus SSE, where SST, SSTR and SSE are defined as follows. SST measures the total variation in the data set. the variation of all individual data points from the grand mean. SSTR measures the explained variation, that is the variation that can be explained, which is the variation of individual sample means from the grand mean. It is that part of the variation that is possibly expected or explained because the data points are drawn from different populations. It is the variation between groups of data points. SSE means unexplained variation, the variation within each group that cannot be explained by possible differences between the groups. We are still continuing with the theory of ANOVA. Number of degrees of freedom associated with SST is n-1, n total observations in all R groups, less 1 degree of freedom lost with the calculation of the grand mean. If you do not understand the meaning of degrees of freedom, you do not need to understand it. Just remember the formula. Number of degrees of freedom associated with SSTR is R-1, R sample means, less 1 degree of freedom lost during the computation. Number of degrees of freedom associated with SSE is n-R, n total observations in all groups, less 1 degree of freedom lost during calculation. So you understand, when we are doing calculation, we are losing various degrees of freedom. The degrees of freedom are additive in the same way as are the sums of squares. df total equal to df treatment plus df error, n-1 equal to r-1 plus n-r. You can check this equality using the various high school algebra techniques that you have learned. You will notice that the r and minus r in the right hand side cancels, leaving n-1 in the right hand side, which equals the n-1 in the left hand side. Recall that the calculation of the sample variance involves the division of the sum of squared deviations from the sample mean by the number of degrees of freedom. This principle is applied as well to find the mean square deviations within the analysis of variance. Mean square treatment is MSTR is defined as SSTR divided by R-1. Mean squared error MSE is SSE by degrees of freedom. Mean squared error MST SST by n-1. Note that the additive properties of sums of squares do not extend to the mean squares. This is a fundamental fact of linear models. MST is not equal to MSTR plus MSE. In fact, MST is not equal to SSTR plus SSE, but SST is equal to SSTR plus SSE, which means if all the things are sum of squares, then the addition holds good. If at least one of them becomes m, in that case the sum does not hold good. Expected value of MSE is sigma square, that is of course obvious by now. And if I tell you that expected value of MSTR is sigma square plus summation ni into mu y minus mu whole square by r minus 1, I am sure you will not ask me the question what is equal to mu I. You will accept it silently when the null hypothesis is true. If the null hypothesis is false, then expected value of MSTR will be not equal to sigma square, where mu I is the mean of population I and mu is the combined mean of all R populations. That is, the expected mean squared error is simply the common population variance. Remember the assumption of equal population variances? But the expected treatment sum of squares is the common population variance plus a term related to the variation of the individual population means, which means it is around the grand population mean. Which mean you take actually depends on the context. Sometimes you take the grand population mean, sometimes you take the group mean, sometimes you take the individual population mean. So, we can say that the n will justify the means. If the null hypothesis is true, so that the population means are all equal, the second term in the EMSTR formulation is 0 and EMSTR is equal to the common population variance. When the null hypothesis of ANOVA is true and all R population means are equal, MSTR and MSE are two independent unbiased estimators of the common population variance sigma square. On the other hand, when the null hypothesis is false and possibly the ANOVA assumption is also false, then MSTR will tend to be larger than MSE. So, the ratio of MSTR and MSE can be used as an indicator of the quality or inequality of the R population means. This ratio will tend to be near 1 if the null hypothesis is true and greater than 1 if it is false. The ANOVA test finally is a test of whether MSTR by MSE is equal to or greater than 1. Under the assumptions of ANOVA, the ratio MSTR by MSE possesses an F distribution with R minus 1 degrees of freedom for the numerator and n minus r degrees of freedom for the denominator when the null hypothesis is true. If the null hypothesis is not true, then the situation is much more complicated with non-centrality parameters coming into picture. The test statistic in analysis of variance is F equal to MSTR by MSE. The linear model, as we know, it is defined as y equal to x beta plus epsilon. In this model, if we include predictor variables containing two categories, then the resulting coefficient beta for that predictor compares the difference between the mean scores of the two categories. Now, suppose we ask ourselves, how can we use a linear model to compare differences between the means of more than two groups? We now use dummy coding to represent these different groups and stick them in the linear model. Let us take an example. Suppose National Transportation Safety Board NUTS to examine the safety of compact cars, mid-size cars and full-size cars. It collects a sample of 3 of each of the groups. The variable measured here is the mean pressure applied to the driver's head during a crash test for these 3 types of cars. The data are as follows. For compact cars, these 3 numbers, mid-sized car, another 3 numbers, full-sized car, another 3 numbers. In order to handle a problem where we wish to compare more than 2 groups, we can start with the same idea as we have used for 2 groups. We choose one group as the base and we create 2 dummy variables to represent the other 2 conditions. The resulting model being mean pressure I plus beta naught plus beta 1 mid-size cars I plus beta 2 full-size cars plus epsilon. Using the coding scheme, we can express each group by combining the codes of the 2 dummy variables as we please. One example is shown here: 001, 010, compact cars, mid-size cars, full-size cars. When the predictors are made of groups, the predicted response will be the group mean, knowing which we can look at the model for each group. Here, when we talk about the model for each group, we do not mean the model of the car. Instead, we are talking of the statistical model which controls each group. Compact cars group. In the compact cars group, both mid-sized and full-sized cars dummy variables are 0. Thus, the predicted response is the mean of the compact cars group. Mean pressure, and that sign above mean pressure is actually a hat symbol. equal to the expression given. Mean pressure I is the next expression and x bar compact cars is beta naught hat. We are looking at predicting the mean pressure exerted on the head of the driver when both mid-size and full-size cars are ignored. So, the predicted response will be the mean of the compact cars group. Full-size cars group. If we examine the full-size cars group, the dummy variable full-sized cars will be coded as 1 and the other dummy variable will be 0. So, the model becomes beta naught hat plus beta 2 hat. Then the model predicts the value of the response equals the full-sized cars group. Full-sized cars beta naught hat plus beta 2 hat. X bar full-sized cars, x bar compact cars plus beta 2 hat. Beta 2 hat is x bar full-sized cars minus x bar compact cars. Mid-size cars group. If we examine the full-size cars group, the dummy variable full-sized cars will be coded as 1. The other dummy variable will be 0. So, the model becomes again something similar to the last case, beta naught hat plus beta 1 hat. Then the model predicts the value of the response equal to full-sized cars group and mid-sized cars, x bar of mid-sized cars equal to x bar of compact cars plus beta 2 hat, where beta 2 hat is x bar mid-sized cars and obviously x bar compact cars. I hope you can follow this argument quite easily because they use nothing but very simple concepts, though presented in a somewhat long-winded fashion. The form of dummy variable coding that we have demonstrated in the earlier slides is the simplest form, but we will see in later module that we can make it even more complicated. So, we want to code them to test specific hypothesis. These alternative coding schemes are known as contrast. We will dedicate a separate module for the testing of contrast in an ANOVA setting. This module looked at possibly the most important application of linear models, namely the case of ANOVA. The theory is vast and do not think that we have finished talking about it yet. There are quite a few subsequent modules that will continue the main idea that we presented in this module.